Hi everyone, I'm just getting things set up so that we can record this next video in our unit on statistical reasoning. So we're working on Unit 6, Chapter 5 in our textbook, Statistical Reasoning. And the second section that we covered was really covering and looking at visual depictions of data. So frequency tables, histograms, and frequency polygons. The purpose of the lesson was to make sure that you knew how to create a frequency table and be able to graph from a set of data using these styles. A couple of words from the vocabulary, and basically they're the same as the title itself: frequency distribution tables, histograms, and frequency polygons. We started and jumped right in with an example where we were looking at the city of Winnipeg, where flooding has been a recurring problem through the years. And what we had was some data that was to show us why this really is an issue. What's happening in the city of Winnipeg is that there's a river that flows through the city called the Red River. And this is seasonally, the river rises and really gives them a run for their money. So the data that we looked at represents the flow rates. In other words, how much water is flowing by a certain spot of the Red River. It's from 1950 to 1999, so basically 50-year sample. It's recorded at the Redwood Bridge in Winnipeg, Manitoba, and they must have some instrument that can actually measure how much water is flowing at a given time. Now, keep in mind that they have had, it's about 10 floods. It's actually 9 to be exact, but to keep things a little bit easier in reading the data, we're going to just go around with the 10 number, 4 of them being severe since 1950. The worst flood was called the flood of the century, and this one occurred in 1997. So our question that we're supposed to tackle, we're going to be given some data and we're asked to show how can you approximate the water flow rate that's associated with serious flooding in Winnipeg. Well, the first thing we notice actually is 1997, which was the flood of the century, as they called it, had a flow rate of 4,587. And then you're going to notice that there are a few other pieces of data in pink, and these guys were the other severe floods. Now, they have kind of helped us with this by highlighting these. So what we're going to do is try to take this data and organize it in a way so that we will be able to determine in an easier manner what is the flow rate that actually causes these floods that go on so regularly in Winnipeg. So we're going to create a frequency table. So what we're looking for then is we want to know the very smallest amount of flow, and I believe that's 159. And we want the largest, which was 4,587. Now, if you subtract those, let me just get my calculator out and do that as well. 4,587 is 159. Gives us 4,428. Now, most frequency tables take the range and divide them into anywhere from 6 to 10 or 12 intervals. So if we divided this one, started with 10, we would get 442 numbers kind of in each one. So let's round it up and let's do it from 0 to 500 and go in increments of 500, trying to analyze the data that we have. So keep in mind that the upper limit of the interval you choose is the place that the number will actually correspond to. And by that, what I mean is if we put in an interval of 0 to 500 and 500 to 1,000, and we actually had 1,000 to 1,500, let's say we actually do have a sample that is exactly 1,000, we will record that one in this one where it is the upper limit, not the lower limit. So literally, if I go back to the data for a second, what we're doing is taking a look at each one of these pieces of data and putting a little mark, just a little check mark to show where it belongs. So for instance, 3,058, if I go back to my distribution table that I have, 3,058 would be here in this one. So it represents the first little stroke that I have. And I go through and make a stroke for absolutely everyone that I have because I'm trying to count up how many years had a flow rate between 0 and 500, how many had a flow rate 500 to 1,000, and so on. And we're using tally marks. Tally marks are an easy way of recording quick information like this. We put them in groups of 5 so that you can recognize it quickly. What I found in the end was that there were 6 here, 11 here, and so on straight down. I would encourage you to pause the video and try it yourself. and make sure that you get the same results. Now, what we're going to do after we have these results is we're going to try and find a better way to demonstrate what these results are telling us. So the first one we're going to do is actually we're going to use a histogram. There's both the histogram and the frequency polygon that we can use to create a more visual or a more attractive or a more user-friendly version of this information. So the histogram, really sometimes known as a bar graph. You'll notice I still have things divided into 500. So here's 500, 1,000. Here's 1,500. There's 2,000. And so you'll notice between 0 and 500, I have 6 times that it happened. 500 and 1,000, there are 11. My number's not very much in the half. It should be 11. This one is 9 times, and so on. So I've drawn a picture of the data that I have for this flow rate. In the second style, we use what is called a frequency polygon, and we're going to use dots. So between 0 and 500, which I've labeled, I'm going to put a dot right in the middle at 6. 500 and 1,000, I put a dot right in the middle at 11, and so on, all the way through my data set. And then I join the lines. You get this sort of herky-jerky line kind of stuff going on. We call it the frequency polygon. Please notice in both these examples that you have to be careful in labeling what the y-axis actually stands for and what the x-axis stands for so that you understand the data when you're looking at it. And so basically, when we look back at this, I guess just to look at our data a little bit, and I think with this one, we want to know what was that caused the serious floods. So clearly this one was one serious flood, and then we had a few more. So we realized as we looked at these that numbers that were 3,000 and higher were where we were getting serious floods. And then we looked back and realized, okay, anything from 2,000 to 3,000 were also giving us serious floods as well. And so basically anything at 2,000 mark and above was seeming to suggest that they would have flooding conditions in the city for this one. So then I looked a little bit more at the issue in Winnipeg. We talked a little bit about the solution that they created, which is basically a big diversion. It's called Duff's Ditch, named after the premier who pushed to have this dug. Basically, it's a 47-kilometer channel that diverts water around the city and allows the river levels in Winnipeg to remain below the flood level so that they don't actually flood the city. The gates are open whenever the city is threatened. And the following video, actually, flooding in Winnipeg, was one that actually showed us some images of that. Because this isn't my video, I'm not going to turn it on, but you can also Google it if you're interested in it. So going back to our data then once again, remember, anything 3,000 and higher was creating very serious floods. And then when we looked at the others, we realized that things that were 2,000 and above were also creating flooding conditions in the city. So one of the questions we had looking at this data, and what I want you to do is to try and answer this inductively. So you take the data in front of you and you look at it and see if you can answer it. It says, are the high flow rates becoming the norm in recent times rather than the exception? So if we look at the data set here on the very last 5 years, now we only go up to 1999 in terms of the data set we have. We'd have to do a little bit more exploring, but let's just give an inductive reason based on this. What we're seeing is that we have 3 out of the 5 years, we've got some fairly serious flood levels. And then when you look at these guys, this one's pretty close to 2000. And actually, when you do a little bit of research, it tells you that anything around the 1,500 mark is where they open the floodgates, just to make sure that even the lower areas of the city are not flooded. So almost 5 out of 5 right here created flooding conditions in those last 5 years. Whereas if we look at some of the other data sets, let's say we're over here, you can see that lots of them are low. This one's just barely beginning, and this one, yeah, we're getting closer to a flood. But it's almost like 1, maybe 2 at the most out of 5. So you can see a trend, at least from the data set that we're looking at right now, a trend that seems to say water levels are getting higher. And especially when you have these 2 significant floods taking place in 1996 and 1997, it leads us to kind of give an inductive conclusion that we do see higher water rates. So once again, histograms and frequency polygons are visual tools that we can use to describe the data that we're actually studying. And it allows us to compare them, at least some things about them, not everything. Frequency polygons are especially helpful if you want to try to compare more than two sets of data and compare one to the other. So that last example that we looked at was about earthquakes in Canada from 2005. So first, we needed to understand what the unit used to measure earthquakes actually meant, so the Richter scale. And so we used this chart to kind of introduce ourselves to the effect. It starts here about 3, where that is a earthquake that is actually recorded seismically on the seismograph, but we wouldn't feel it. And if you read the description for each one of these levels, you'll see that it becomes increasingly more obvious. You start to see things are moving when it gets to 4 to 5. Things are starting to move if they're unstable. There's considerable damage to weak buildings from 5 to 6. And from 6 to 7, it's difficult to stand. Buildings, ordinary buildings, are collapsing. And then from 7 to 8, you're getting very significant destruction happening. So let's take a look at the data that we're given. We're being asked, okay, 2005, 2006, 2007, 2008, 2009, which one of these had the most damage? So now we could look at this and try to examine, well, when did damage really start? If I went back to what I had, damage really started about 4 and higher. But, how do I measure damage? Maybe I need to take a little bit of a closer look at these ones. And so what we did was created a frequency table that we could use. And we listed all our years here and all the different Richter scales that we had, and we started to put them in. We came up with these numbers. I think this one, though, just to explain, was the wrong number. It should be a 5. But we went through and saw that there were 5 earthquakes in this range, 3, and so on. And then we took totals. And it kind of came, obviously, that 2008 was a very disruptive year. There were 25 sort of earthquakes in there. Now, another thing that's kind of important for us to see is both these ones with the stars have earthquake numbers at 11. But the question is, did they produce similar amounts of damage? Well, if you look at them, the significance difference here is that we did have one earthquake between 6 and almost 7. This one produces a lot more damage. So while these numbers 11 are the same, they're not really the same in terms of the damage that they caused. But all of that to say, 2008 does look pretty significant. 2009 has its moments as well. And so what we did with our data was put it on a frequency polygon. And we put 2008 in a frequency polygon that's red and 2009 in a frequency polygon that's blue. And this one depicts for us kind of clearly that the 2008 readings, it really had more damage. You see more damage being happening as it kind of slides over the Richter scale a little bit more. So that's just introducing you anyway to histograms and frequency polygons. They are a really useful visual tool. Do keep in mind, though, that in these pieces of information, we are no longer really clearly showing minimums and maximums and medians. And so they aren't easy to determine. Histograms, frequency polygons, distribution tables, they have their place and they have their purpose, but it is not necessarily towards the central tendencies. So there you have it, an introduction to those ones. Take a look at your homework and let me know if you have any questions.